Okay, so now this promises to be a 1.5 hour conversation. But I tell you that if we run out of steam or run out of good talks, we'll just take another coffee break. So don't worry about the fact that it's planned for 1.5 hours. It's going to be. It has to be a nice talk, actually, nice discussion. The thing that I was asked several times during this workshop is, why is there no time for discussion? And actually, there was hardly any time for discussion. All the talks were very good, precisely in an hour. And so how much time do you have left after you have only 1 hour for an hour speech? So the one of the things I would like to do now is to give the floor to the audience and ask you any questions you like. But to a large extent, you're part of the audience also. So don't hesitate to ask each other questions. The second thing I'd like to do, and not only questions, but just get more to the depth or whatever you think you need to get to the depth to. The other thing I'd like to do is to ask each of the panel people, the speakers in other words, one simple question. If you would have to explain to somebody outside of this room what the key message is, or the key thing is that you learned or would like to convey to them, what is that? So, now, having asked those questions, or having given this short introduction or whatever, is there anybody in the audience? There should be in the audience.
Jan, there's nobody left in the audience. We're all
So is there anybody in this room? But Kevin already put up his finger. Yes, go ahead.
Yeah, actually I have a question for...
we need more than one.
Yeah.
Okay. Is this one working? Okay, good. Actually, I have a question mainly for Brian. So, it is about the people's prediction on people's prediction. So yesterday you gave a very interesting talk mentioning about the bar model, which you started about 20 or 30 years ago. Well, talking about the people, when people were deciding whether to go to a bar or not, they predict how many people will go there. So this is a very nice example of the people's prediction on people's prediction, and then they take actions based on such kind of predictions. I'm thinking that in the market, probably when we are doing investment, we were, many of us may be doing the same thing. It's just like, say, when the market is going up, with the common sense, we all know that it cannot just go up until forever. Sooner or later, it will go down. It's like, there may be a crash if it's going up very quickly and then for already long enough time. Yet many of us may still choose to, jump in. It's not because we believe the market will go up until forever. It's because we think other people will buy. We still have a chance to make a little bit profit before the market crash. So that may actually, in my personal feeling, is like that may actually make the later crash even worse. So when we are trying to model the market behavior, we probably need to take such kind of thing into account. Then here comes my question, is like how to model the people's prediction on people's prediction. I mean, if we just use the random model, may not be so helpful, right? But how to model that? And if you want data, how to collect the data? Thank you.
Well, actually, I think that's a really profound issue. And it's right at the heart of where economics is at the moment. John Maynard Keynes was very much interested in stock markets and made an awful lot of money. And he remarked, and this is in the 1930s, quite a long time ago, he said the market depends on people's predictions of what other people's predictions will be. And that principle, since another person who's made an awful lot of money in the market is George Soros, and Soros has deified this as the reflexivity principle. But just to go to fundamentals, economics, standard economics has always said that we can form a predictive model, and it does it kind of by sleight of hand. It's basically saying there's, in physics language, there's some sort of an attractor. Everybody knows what that will be. everybody knows that everybody knows, and assuming that everybody knows that everybody knows, and we're all using the same predictors, that outcome will come about. Therefore, we can be sure we're predicting that, at least statistically. It turns out it's a dreadfully bad assumption. All economics theory at the moment is based on it, and where economics is refuting that at the moment. Economics sits in a kind of Euclidean geometry history, and just at about this time in its juncture, it's refuting this axiom that you can predict at all. So basically, my answer to your question is, you can't make assumptions about what other people will predict other people to be doing, because they're trying to make assumptions about what you're trying to do, and that is infinitely regressive in logic. If I predict what you might, if I try to figure out what you might be thinking, knowing that you're thinking about what I might be thinking, and I'm thinking about what you can go 10 or a million layers deep and you still haven't got to it. So the modern approach is to say, we just don't know. That's called Knightian uncertainty, and we're only finally coming to grips with that in economics. But it's like refuting Euclid's fifth axiom. It gives you a very different economics, gives you an economics where people just don't know. So what do? They blunder around. Everybody's exploring all the time. Maybe they will coordinate on something, but everybody's trying to figure out what other people are going to do. I sit in Silicon Valley. This is not abstract stuff. In the Valley, you might be trying to launch some new product, some new technology. You haven't a clue who your competitors are going to be. You don't know what the regulatory people are going to do in Washington. You don't know what bets are going to get made in between. You still have to launch 2 years ahead. So the economy consists of people exploring, blundering around, half in the dark, and so there's a natural Brownian motion to the economy, and economics is starting to recognize this. The fundamental place for the economy is non-equilibrium. And this is a huge sea change in economics. I'm sorry I'm going on a bit about this, but this is right at the heart of where economics is changing at the moment.
Jan, I just have a comment. Go ahead.
I'm going to make one comment very quickly. That in the experimental economics literature, there are some games in which it is known that optimal play can be had in, say, it'll be set up for, say, in 6 or 8 or 10 look-ahead steps. Yeah, you can actually figure out what the optimal behavior will be. So you can then use backward induction to figure out what is the best way to behave. And these are game theoretic setups. So basically, so my payoff depends on what my opponents are doing, etc. So it turns out there, if you look at this is nicely summarized in the recent book called Behavioral Game Theory by Kammerer. So in that book, he goes through, and this falls under the category of, I think it's experience-weighted learning games, and you'll find something called nth order rationality. So nth order rationality is this adjustable n, where you can say how are people actually doing the computation. Now, there the interesting result that falls out of this is that you actually can experimentally resolve how are people playing the game. And it turns out that maybe some of you probably have seen this, but there are a lot of people who use, in fact, zero look ahead, who don't imagine that people are strategic at all. Or then there's some people who use 1 period 1, period 2. But it turns out the average is about 1.5. So in fact, people are using very far from the full 10 period whatever it is look ahead. So in fact, when it comes to forming these predictions, people are very far from the common knowledge perspective of basically everybody believing that everybody else is rational.
Actually, what I wanted to say goes along with what you're talking about, Ram. Let me go back to a classic. It used to be said that you couldn't have self-reproducing machines because there was this infinite regress. You had to have a description of the machine, and then a description of the description, and then a description of the description, and so on. And that paradox was resolved by using 2 levels of description. And, so in effect, von Neumann wound up with a chromosome, although he didn't treat it that. And I think that goes along with your discussion, which also has been done, by the way, with respect to the prisoner's dilemma. How much memory are you allowed, and how do you use it? So I don't think this is a hopeless problem. I do think that this business, and along the lines that you're talking about, that if you begin to discuss how far back can you look, and then, and I haven't seen this done, but it certainly is possible, if you then use levels of description, then I think there's something that can be done along those lines. And this, personally, is one of the reasons I'm so interested in language acquisition and evolution, because I think this notion, we begin to get along these lines at notions like meaning, that the next level up is sort of the meaning of the details of the level below.
I have one further comment. I mean, go ahead, Neil.
Yeah, no, I was going to say the beauty of being a complete novice in economics is that I can make up another story. And so the answer to what I would imagine we're all traders, and all these different books have been written about, one level beyond and two level beyond of thinking. They're all sitting up, I was going to say in Borders, but Borders is out of business, so Barnes and Noble. They're all lined up there, and we're all traders, and we go in there and we choose the two books that we want out of all of that. What's going to happen is just because people want to write different books, you're going to get all sorts of different books written. The two books that we choose might have things that are in common. Each one of those chapters is really a response to a different type of pattern that you might see. So you can imagine a very cartoon version of how we end up with we each have two books. We use the book that's working best, and we look up the chapter that gives us the conditions for now, and we respond to that in the way that we do, and that then encodes the strategies following the information.
So I just want to make a somewhat technical point. So on this business of nth order rationality, it is the following the case that in the old swarm system that Chris Langton put together, it was possible. Well, let me step back and say, why do those of us who build computational models, why do we do that instead of using this mathematics? Well, I agree that mathematics is too hard, but basically we were somehow unhappy with the expressiveness of mathematics. We have this more supple device of the if then else rules of the agents. But now there's actually something we do which is very phony, where we build the agent-based model with no mathematics really, just the agents. But then in the heads of the agents, what do? We put in mathematics, right, for how to behave. So it turns out that in Chris's original SFI modeling platform called Swarm, he actually made it possible so that every agent could have in its head another multi-agent system, which was very novel. I only saw it used once or twice. It was actually not something which was well exercised by the community. But so it turns out I have the following. I have one student right now who's just finished his degree, who's done the following. He says, okay, in some sense we have crude models in our head. So he does the following chain. He says. He has an n-order multi-agent system. Then he puts in the heads of all those agents, he puts n-1 agents. And in the heads of all those, he puts n-2. And he goes all the way back to basically you get single agent models, and so then those are basically going to be decision theoretic models as opposed to game theoretic models. So you can solve that, then he goes backward. And so it turns out there are a whole bunch of models that actually do converge in that respect, that they actually, there's a certain class of behaviors which would converge in this hierarchy of having n-1. And so yeah, I think that now whether that has to do with anything with reality is unknown, but this is possible to render it computationally.
Kevin, does that give you some insight into what you're...
Yeah, I think I need to like this. It seems like they are telling, okay, they are answering the same question by telling slightly different story. Try to understand this. Basically, okay, basically my understanding is that Brian side is like, I don't know whether I have got it right or not, but my feeling is that Brian is saying that basically if you try to model it, it is kind of risky. You may want to put it the next way is like each agent perform without really accurate information and half blindly. But I'm still thinking like, okay, if we want to do, say, agent-based simulation, we still need to have a certain kind of distribution, like what kind of information or what's the meaning of a half-blind here. otherwise, when we are doing the coding, say for example, if we want to finally put it into a program, we still need to give each one a way, you know, in a certain number of lines of code to decide what's the meaning of half blank.
Of what?
That's something I still haven't got it yet.
So the meaning of?
I mean, like half blindly, we are doing almost everything half blindly in the market,
Half
right?
blind.
Half blind, sorry.
Yeah.
Yeah.
You have more microphones here.
Can I make?
There's one there, there's one there. We need another one.
Okay.
Is there another microphone?
Can I make one comment? Just.
Yes.
So, one thing that can limit the regress is sort of a, I don't know if it's a trivial way to limit it, but it's certainly something that would require experimentation in the world, is that I think people are fairly limited in just how far they can regress. And so I think that there may be just ways that people behave that you can sort out and do it in a very practical way, you know. But I'm not going to talk about that because I don't know very much about that. But there are things that if you put a lot of interactors together, and if you represent them, I mean, you can represent them as a network if you want to, but for my purposes I will. So you're going to put the interactors at a vertex and you're going to indicate their interaction by having an edge. Depending on it is not just dependent on the graph structure, like how the dynamics of this thing work. It also depends on the functional structure of what's in those vertices. It depends on the question you're asking, but the dynamics of some process going over this structure can depend on both. And so, just to make an example, and I don't know how well it pertains to this question exactly, is that if you have a single threshold, like suppose you have a bi-threshold, but it could be any kind of threshold, a threshold about whether you're going to be infected or not. You know, for a given exposure, and you look at the spread of infection, or you look at the spread of buying behavior in the network in the case, then systems that have their theorems that you can prove that talk about for any systems that have these threshold functions, they have certain kinds of properties that they'll exhibit in their phase space, and it depends on the graph and it depends on the function, but there's a thing that happens when you have a threshold function at those vertices. If you put a bi-threshold function, so a bi-threshold function, there's one threshold for buying and there's a different threshold for selling. Or there's one threshold to start smoking and there's another threshold to stop smoking, or any number of things. Those have completely different properties. And in fact, the bi-threshold systems, this is ongoing research, so I'm not exactly sure how this is going to work out, but they appear to have very structured, featured, fixed point features. So it could be that for certain kinds of decisions, if they get complicated and you're playing against one another, the system itself, not because of what one person is doing and entering into regress, but because of the way the system works conjointly, that the system can enter into, you know, certain kinds of structures that would then limit the behavior of the people engaged. And so this regress, it might fail to become infinite for many different reasons, okay? I mean, it might fail because the system just tightens up when you start to enter into it, and that limits the behavior of the players going forward. It could be, so there's, I don't think, anyway, it's like sort of like the infinite question for this kind of modeling. There's no question about that. But I think there's a lot of possible things that could constrain how these outcomes come out.
And one last comment on this. Standard theoretical economics got built on a kind of Enlightenment idea that all problems in economics can be logically well defined, and the people in the economy respond with deductive logic and can do that, have the ability to do it. The reason I wrote that L for all paper in the first place was to logically define a problem that had no logical deductive solution. There isn't a logical way to solve that problem. And so economics, for the first time in its history, as I said a moment ago, is facing this problem. It's built on a set of assumptions. It says all problems are well defined. that all solutions are well defined. In the actual economy, things are not well defined. John Seeley Brown in Silicon Valley puts it not very nicely. He says in the old days, the challenge for management was making products. Now the challenge in high tech, he says, is making sense, S-E-N-S-E. You're trying to figure what problem environment am I in, what am I trying to do, who's playing in this. None of those are well defined, and we haven't got yet a finished theory in economics. We've got a lot of behavioral things, as several people have said, but we haven't got a finished theory of how to deal with the unknown, or what you might call unknown unknowns, or what we would call Knightian uncertainty. And this is a huge sea change. It leads you immediately to non-equilibrium solutions. Everything changes. And I think this is wonderful. And I think that this is why complexity ideas, many of which you've heard, they're all about trying to figure out what to do in a space that isn't too well defined. How do you blunder ahead, explore, change, improve? And so this is a huge thing. The core of people in orthodox economics haven't got that yet, but the field will change. If you think that you can put probability distributions around everything, solve it that way, then you haven't got it. That's the old thinking, and that's just analytical convenience. Really, in most economic problems we face, we simply don't know. I may be off the freeway in some tiny town in California, and I'm wondering, how do I get to the freeway? And I haven't got a map, and I haven't got GPS. The problem's not well defined, but we face these problems every day. What do? We ask people, we explore, we do some reasoning, the freeway must be over there, so. But it's not a well-defined problem. Yet economics would say probability distributions and so on. It's all nonsense. There isn't analytical solutions to most things, but yet we muddle on. And there are a lot of behavioral solutions. So the field is going to change, and it's changing rapidly.
Peter?
Okay, I'd like to bring up another topic. Just to move away from the infinite regression thing. But actually it's also picking up one of your questions, Brian, to Neil. So in my first introduction to complexity research was in 1995 when I was visiting Chris, among others, in Santa Fe. And one of the things I was thinking at that time was people are just throwing in algorithms to explain complex behavior, and there's all kind of reasoning, but there's no real theory. And it touches a bit on what you just said. There's probabilistic methods, there are algorithmic methods. There's everything, but there's no real theory of complexity. That is a danger, I think. It can be good, but it can also be a danger because it is like with computer science. If it's everywhere, it's nowhere anymore. If complexity is everywhere, then in the end it's going to be a non-issue. Because you will have just, sociology is doing the sociology again, and biology is doing the biology again, and the whole notion of complexity disappears. So unless there is some kind of underlying fundamental principles which we can get our arms around, and which we can formulate in a way that makes sense, it will disappear. That is my prediction. So I tried to do a bit of that. In 1995, at that time with Steen Rasmussen, and also a bit with Chris, and since then I've been trying to do it in many different ways, trying to see but I couldn't. Now that doesn't mean anything because I'm pretty limited in those things, but I think that is something that I'd like to bring to the audience and to my fellow presenters. Do we expect that there will be a theory of complexity? And if so, what could it look like? Or do we expect it will never be there and it's just a set of algorithms that are going to change over time depending on what kind of hype you're into? Which I can understand because, okay, I'm not going to go that way. But anyway, so that's my question. And so I like to bring that up because that is something that's been bugging me for this now 20 years. And so I'd like to open the floor with that. Anybody wants to say something about that?
Actually, I have a loud voice. I don't think I need that. Is that true?
What?
I'm a great believer in theory, and I think, however, that it's very important as we strive for theory in this area to make a distinction. I said this briefly before, but I'd like to emphasize it. There are two kinds of complexity, two different strands. One is what I'll call complex physical systems, and that's the starting strand at SFI, where a bunch of physicists were interested in things like emergent properties, the Ising model and all these models. And there, of course, there's a bit of theory in that area. The other strand, which I think where my interest lies, is complex adaptive systems, where the agents don't have fixed rules, they change over time, they evolve, and so on. And that distinction is important because otherwise, if we talk about theory, I think we're going to find ourselves in a kind of strange miasma.
Okay, so let's pick one.
Okay, complex adaptive systems, that's where my interest lies. I do believe there can be a theory of complex adaptive systems. Now, I would be skeptical about a grand theory. That's another story. But to have enough theory, for instance, you know, and this is just wild speculation at this point, but I think it's possible to know more and build a more theoretical model of how I find lever points. It's not going to be complete, but it'll be better than letting us do by God and by guess. And to say this in a slightly different way, Brian made the nice distinction that for a long time our view has been that we can create a deductive system, say a set of axioms and proof theorems and so on, and those are very nice theories. It doesn't seem that we're going to be doing something like that in this context. The other extreme is what people sometimes call the first Harvard law of biology. You take carefully selected animals and you put them in designed positions and experiments, and they do what they damned please. Now, somewhere it seems what we can do lies between those two extremes. And I think it's terribly, terribly important.
So, Heiko, you were going to say something.
I was about to ask this question anyways. Now you brought this topic up. I was wondering whether, because, okay, first of all, I found all these talks in the last, yesterday and today very interesting. And what I noticed is there are a lot of patterns that people see in, let's say, financial time series, or let it be earthquakes. So you see similar phenomena in different applications, in different domains, different disciplines. So I was wondering whether there has already been some effort to kind of, in a systematic way, let's say you build a database where you describe these different phenomena and try to classify different kinds of complex systems, where you, so to get an idea of what kind of classes of if there are any different kinds of classes of complex systems. So to get a bit of a structure into this, whether this could kind of help to kickstart this, I don't know, if this would help finding a theory.
You are aware of the work of Jeffrey West, who has been doing that for some of, going all the way from mammals to earthquakes, if you like. So I think that there is, but correct me if I'm wrong, there is a tremendous amount of organization already going on in filing complex behavior in all kinds of systems. What I'm asking is, and that is important work, but that is, let's say, the analytical work. But trying to understand why it's there requires theory. So what I like very much was what Neil was doing. So he said, okay, I observed this and this, and it all comes out down to 2.5. Now let's think if we can understand why it's 2.5, and then look for this kind of governing principles that that recur in all these different systems. But that's only step one. That might hint to a theory, but somehow we refrain from making maybe just we have no time, or we don't want to really think about it, or it's too hard, or maybe it's just idle to think that it will ever happen. So my answer to you is yes, I think that's happening, and my question remains. So, is there any hope for a theory, and if so, well, are we going to try it?
I think an important part of this is these things is, say what Jeff is doing, these are snapshots. And what we're mostly interested in, just as you say, is why did those snapshots occur? And what's going to be the next snapshot and the next? And that's, my feeling is very strongly that this is Darwinian. You don't understand species until you understand the ontogeny in that setup. And I think in these systems, we're not going to understand them until we know the ontogeny, until we begin to strive for that. And that's very different from taking these data snapshots.
We had, this is a problem actually that came up in the early days in Santa Fe, as early as 1992 and 93. We had an awful lot of reporters coming there, even 1987, and there was huge fuss made over complexity. And they came back about 5 years later at some conference we held, and they said, "Where's the theory?" And there wasn't really any coherent theory of complex systems. And we had a good colleague of ours, beloved of us all, Stu Kaufman, who always talked about complexity theory and searching for grand theories of complexity. And so we all got immunized in Santa Fe against thinking about anything like that. We think, oh my God, we'll leave that one to Stuart. But I agree with actually several people here, Peter, and what John said. It's early days, and if you look at reductionist science, say from the time of Galileo on, trying to understand these big phenomena in terms of smaller causal explanations of how the elements work and how those elements work, it took 3-4 centuries before Maxwell's system or any other system, Einstein or even Newton, took several decades for these explanatory theories that you could see could explain an awful lot. So I think it's very early days where you're looking at from the ground up at how things form. Nevertheless, I do believe that what we're seeing is what I would call a few motifs. Complexity isn't just about elements creating patterns that those elements react to. That's my favorite definition. Everybody has their own. It's also, complexity is about the propagation of change. And we're seeing we can get second order transition, phase changes or first order ones. We're starting to categorize, or the field as a whole. We're getting these little toy models, like Ising model types of things. Some of those are appearing, and when you start to see the same models crop up again and again, you know that it might not be getting real theory of complexity, but you are getting the outlines of where the landscape is or where it will be. So two things: early days. I don't think there will be a grand theory. Maybe there might be, and but a lot of small motifs coming up, and we're recognizing those. I can't resist saying that Stuart used to go around looking for a fourth law of thermodynamics. This is telling tales, but I have to just say I'm terribly fond of Stuart Kaufman. And he was waiting to hear whispers from the grave of Carnot. And the wags at Santa Fe always said, well, Stuart's waiting for whispers from Carnot, but Carnot's shouting in the ear of Walter Fontana and a bunch of other people. Grand theory, not yet, probably never, but a lot of little motifs.
I just have a couple comments on this general point, and to say that my comments will grow out of the following neural economics framework, but it'll be a little bit, I guess, kind of being skeptical of what Peter proposed. Here's how it goes. That if in fact in economics we have today the Walrasian theory, and we know there are many problems with the Walrasian theory, we need to basically have a non-Walrasian theory for how markets work. When it comes to the theory of the firm, Brian will know that we have the Coasian theory of the firm. That thing is under massive assault today. We need a non-Coasian version of the firm. When it comes to game theory, when it comes to strategic interaction, when you think about it, what is the Nash program of game theory? The Nash program of game theory says, and there's a very great, by the way, there's a great interchange between John Holland online, where it's recorded versus Ken Binmore from about 15 years ago, in which John asserts that the rainforest is never in equilibrium, and Binmore says the only thing that can happen in a real economy is going to be either pure strategy or mixed strategy and Nash equilibrium. The caricature. So the point is, the Nash program of game theory is the following. It says, if there is a macroscopic regularity, it's due to agent level equilibrium. There can't be any dynamics at the agent level. That's against the Nash program. So I think that seeing all the dynamics we have in real models means we need to have a non-Nash game theory. So we need to have a non-Walrasian theory of markets. We need to have a non-Coasian theory of firms and a non-Nash theory of games. And when I gave this talk, when I gave that perspective recently, a very famous economist came to me and said, "It sounds like you're telling us we need to start all over."
Yep.
Now, in that context, I framed that talk. I titled that talk "Non-Elephants," to do justice to Ulam. And now I think that there's a point of Ulam here, is to say that Ulam said there can never be a theory of nonlinear dynamics, because it's a theory of everything that's nonlinear, and that's everything, right? So I do wonder, John, if complex adaptive systems is just everything that's not a simple adaptive system. I'm not sure we're going to have a theory of that. Okay, so that's my.
Well, let's see. Let me take a giant jump. I'm going to make all the accountants in the room happy. I think the greatest impact we could have on the world right now is to change the notion of accounting. And the way let me give you an example. It's not legal in the United States, but if you could have a lottery for each research project where you're making a bet and you could buy a lottery ticket, and this becomes open to everybody. Notice what happens. Immediately you get money into the bottom line, partially dependent on your reputation, but just as in the lottery system, you're making a bet on the future and the money goes into the bottom line. Now, no research organization, now every dollar you put into research is money lost in effect in that quarter. And so CEOs in effect say, oh, well, if I have this research program, I'm impacting the profits. And, you know, as every CEO knows, about 3 quarters later, if you don't show a steady profit, you're out of a job. Okay. On the other hand, if I had this lottery for every research project, if I'm clever, then I get more money coming in than I get from any other source. As, you know, the state lotteries make amply clear. All right. If we could change accounting procedures to do something like that, so that we could have either a virtual lottery or something like that, then suddenly this 10-year horizon, and John Seeley Brown managed to do that at Xerox PARC, but then in a very unusual way. But then, if we could make that change in accounting, just see how much it would change, say, in the United States or most places, what the effort would be for long-range research. And in my opinion, that's central. This whole business of being able to prepare for the future in that sense is central. That, in my terms, that's a huge lever point. And so my feeling is not that this theory of complex adaptive systems is everything, but that in fact I want to look at particular kinds of adaptation carried out in particular kinds of way. You saw me concentrate on recombination of building blocks. That's not everything. That's rather a limited class of adaptive systems. And it's with that kind of background that I would expect to be able to do something theoretical, and I've said before, and some know, the thing that really got me started in this was long ago when I read Fisher's book on a genetical theory of natural selection, where he showed that you could do something mathematical about systems in which most people thought nothing could be done. I feel that if I expand that and get this notion of recombination, that I can still do something theoretical. And while I won't try to make the bridge here, there is a real relationship in my mind between this sort of lottery system for inventing things and the way of saying, well, what should this lottery look like, virtual or otherwise?
So if you allow me, having all those brains here, I'd like to make use of that. So there were two parts in my question. One was say, okay, do we expect that there will be, is there a theory or what? Okay. So now let's be academical here. Let's assume that we will not find a theory. Will complexity research then go the same way that, for instance, self-organized criticality research went? I showed you the graphs, right? It went up and then it basically disappeared because, well, it's everywhere, so it's everywhere. I mean, who cares? It's not, it doesn't really have predictive power, only on averaging over many, many, many things, but, for an individual, it doesn't matter. So, my question, my second, which was related to the first question, my second question is, assume that there will be no theory of complexity. Will complexity, and we know that complexity is everywhere, will complexity research then disappear?
I, for one, think yes. We've seen, you mentioned, before there was catastrophe theory, even further back, and then chaos theory and so on. And these things, at first, we thought there was some predictive power. People even, with catastrophe theory, there were some very fanciful things said, but none of them backed up really in the long run. And so I think, yes, I think complexity, whatever version you're talking about, will largely move into the background unless we have some results that go beyond metaphor.
I'm not so sure that I agree with it. There's a very nice paper by Leon Cooper on the brain. And he says it's a very complicated thing to handle, to think about, to even start to think about theories. But unless we look for a theory, we will never understand it. And the brain is not going to disappear if everybody thinks that. So if complexity is really a key issue in the way things function in this world, and emergence is a key issue in terms of that you want to understand, I cannot think that that kind of research will really disappear simply because it seems to be too difficult to handle.
Question now to you is, did you, when you said that, the brain, is an issue that's not going to go away.
No.
and there are lots of complex systems. I think the critical edge there is whether it is, the notion of complexity has enough of a, what do I want to call it, solid object like the brain to keep it focused.
Okay. I'm not saying that complexity goes away.
No.
I mean, chaos hasn't gone away, and self-organized criticality is still there, and all the other things are still there.
But so is
but basically the research, it has no predictive power or whatever, and basically the research in it disappeared for whatever reason. And my feeling is that the reason might be because there is no kind of governing theory or something behind it. But that was the question.
Just to interrupt, there's one question in the audience here. Whatever, the other part of the audience.
I have a jumble of thoughts in my head over the last 2 days, but some of it also came up in the discussion just now. My last complex systems model was 20 years ago. It was basically ripped out of Goldberger's book, and I have lost touch with the literature, but I was really gratified to be in this sessions these last 2 days and see how far it's come. And since those 20 years, I've been accumulating a lot of other desidera, is it? Just kind of odds and ends, and now I'm trying to see how it helps me make sense of where you've come and where I've come. And I do a lot of qualitative work now, and I do work on creativity. I try to understand creativity in video games in particular, and the three things that sorry, to go back to John Holland's first talk, I liked a lot the idea that you're trying to establish some structures, because I now work in a management department, and I deal with theories of the firm a little bit, and I see the boundary issue as a very important thing to management scholars. So I felt, my first thought as well, that there are things from other disciplines that can also sort of help shed light on why boundaries form in societies, communities, and firms, and I'm sure there's some complexity studies that have collaborated with such people, but I hope for more of that kind of close ties to the mother disciplines, as we call them, where some foundational social phenomena are at work, or organizational phenomena. And then thinking about creativity, I felt that in my own research, which is highly inductive, I see three things which are I can barely grasp at, but I feel are somewhat important as far as accounting for innovations. One is meaning, making of meanings of things to different people. Another is the context. Context shifts and provides a space for innovations to occur in. Combinative ability is very important, recombinations. And when I look at all the classes of models presented, I see a very strong modeling methodology at work. I fear for its also, if you make it too general, then where does it go? And I look for that sort of more, some application that allows you to understand deep structure as well, and structure in even an individual mind, right? If you understand how one person thinks about things, then maybe you can build these predictive models, or at least models that account for why an innovation occurs or when it occurs. And so I guess the one example I can think of that would grasp all this is sort of Steve Jobs. You know, as Steve Jobs, can your model predict the emergence of Steve Jobs? And it can predict the effects of the emergence of Steve Jobs, probably. But is it complex? Is Steve Jobs complex, or is he simple? I don't know. You know, it goes back to one of these game designers I was interviewing, and I asked them, is creativity and combinative creativity in your field, is it just like in engineering where it's just some code books and you just draw from these code books in different ways? And he says, yeah, but it's a really big bunch of code books. And so that's the thing I worry, is how, you know, you can't account for all.
What for the cookbooks counts is also for, probably there are zillions of Steve Jobs around, but the niches in which they are not fruitful enough to emerge, so to say.
Yeah, so that's the context, right? The context is not accounted for, doesn't account for that innovation. And so these are the things I'm sort of reaching for myself. So the two things would be meaning, forget meaning, it's impossible to understand. Context, context of operation, context could be multi-level, as John put it. And the third thing would be imagination. You know, what is the widest set of code books your models can account for to allow for that emergence? So just some thoughts.
Well, that sounds like a very clear question.
Well, I'd like to just say I'm not sure how you would predict Steve Jobs if you don't even know what Steve Jobs was. You know, I mean, I don't know what you'd be predicting, frankly, and I'm not even sure that the role of what would make this useful, or I'm not sure that the job is to predict Steve Jobs. I mean, even if you did know what he was, I think you know what he did. But I'm not sure. I don't know how to. I wouldn't even know how to approach even thinking about that question. But I can say that if you have a given functionality, it's not meaningless to take it and abstract it, to take the notion of a given functionality and understand in a lot of detail in many abstract maybe settings how that functionality plays out differently because the contexts are different. I mean, just making that point clearly is valuable, and it's by no means straightforward. And I think it counts as science. And I think if you tie it back to real problems, I think it's important. Sometimes the answer that I think will be delivered is, don't ask that question. That question's hopeless. You have to ask a different question. I don't think that's a meaningless thing to provide. You know, and I think it can come from the kind of, in fact, it does and has come from this kind of work. So I you know, or where the boundaries of a method are. You know, I mean, this recombination methods. Yeah, maybe they are limited. You know, they seem to be fairly effective, but maybe they are limited. Well, it's nice to know that they are, right? I think that's.
But you know, you can. Jan mentioned niche. And notice that if we move this from conscious humans back to ecosystems, then the original attempts at theory in that direction were called food webs. And they were simply a matter of who eats whom. But there is some theory of food webs, even mathematical. Now, can we enlarge that to get a larger notion of niche that allows recirculation of resources and so on? I don't think that's impossible by any matter of means. It doesn't depend on consciousness in the usual definition or anything of that sort. And if we look at that notion, then we can't predict Steve Jobs any more than we can predict the origin or the emergence of some new species that hasn't been there before. But we can say something, and this is along the lines that Jan was talking about, that the situation is favorable for things of this class. And that, I think, is something we can do something about. We can say something. We know that the new electronics, quote, new electronics, opened up a lot of possibilities. There was a niche there. Whether there would be an iPhone is another story entirely. But the fact that there was a possibility for devices that were quite different from telephones of the old style, that was pretty clear. And so I don't think these things are hopeless. I think, but as you said, we have to be careful about the question we ask.
Okay. We have about 20 minutes left. And one thing I'd like to hear from each of you is what message you would tell outside that this workshop was about, or what made it worthwhile to you. And so there's 7 people here. Well, that can be very fast. There's 7 people here for 20 minutes. That is a little bit less than 3 minutes, but we don't care about 1 minute more or less. But maybe
first, Jan, I have a suggestion. Yeah. Why don't all of us move down to the audience move up here?
Well, take some chairs with you, go ahead. But maybe I start with you, Neil.
Yeah. So what's the remit? Am I meant to say something that I've learned or a message that I think I...
If somebody asks you, what made this worthwhile to you?
Right, okay, got it.
That is...
Oh, definitely, definitely
the
variety of takes on what complexity it is and how it should be tackled. And I think they're all valid. And, you know, I've got my own personal one, and it's sort of unmovable because I'm limited. It's the only way I think about the world in a kind of physics way. So, but I can absolutely see where all the others fit. It's things that I just can't do. But that's what I take away, that there's a diversity of views of complexity, which is, well, maybe it will help the field, maybe it will hinder it, I don't know, but certainly there's a diversity.
Okay, well, that's... We may come back to you and ask you to expand a little bit on that, but maybe I'd ask John.
What I'm going to suggest is, because I've been saying a lot anyhow, is to skip over me and let some of the others say.
You'll summarize it for me then?
Oh, yeah, exactly.
Okay, Jing, maybe. Take a.
Yeah. You have a soft voice.
I don't know whether this is a kind of take-home message or not, but it's actually a question to me too. So should I just ask the question? Yeah. My background is computer science, so the first time I I know complex system is when I read the book Complexity, written by Rowe, and it was so interesting. And then I begin to look at this area, and I found there are lots of multi-agent modeling research on complex system, and I also did agent-based modeling and to understand the first word is combinatory optimization problem. And then, but then I get, when I want to move on, and I found there's some difficulty there in mathematics. And so at the time I want somebody to help me how to prove this system to converge to the solution. So, and then after I graduate, I got my PhD, I went to the mathematics and system science academic, which there are a lot of mathematicians. So I think there should be somebody that can help me. And then later on, I actually stayed there till now. So, so now I don't know what. Sometimes I just don't know what I'm doing because being surrounded by the mathematicians, sometimes I found, oh, is my research scientific? Sometimes I'm wondering that, because if you listen to their lecture or look at their paper, then you'll find that they want everything to be proved seriously. So if you present some result to them and just by simulation result, they might not listen. They might not think this is a complete work. And in the beginning, I was very much amazed to their ability in mathematics that they can make all the results look so perfect. I mean, just like the end of this. But then later on, I found actually what they can prove is very limited. So they have to make a lot of assumptions. And then sometimes it will make the problem totally different than what you want. So so sometimes I feel very confusing, and I don't know whether I should go on the way that is to depend on computer simulation, because if I use computer simulation, I can do much more than if I want to rely on a very restricted mathematical model and the analysis result. So should I stay there and wait for the mathematician, or should I just go on and by just looking at and making some computer simulation? So I just feel a bit confused, and but being here, I feel, computer simulation is I think I should continue to doing this because then I can try many interesting ideas, but without worrying that whether this can be proved or not. So I don't know. I just want to hear more from you, experts and scientists, great scientists.
It sounds like a question that you might want to help answer, but I have just one comment. Listening to your talk yesterday, I think you should go on with doing what you're doing, because that was such a superb talk that whether it's theoretical or mathematical is more, to me, that it's not that relevant. It is the kind of originality that you put into it that is the key.
Su Guaning, by the way, talking about this, was very interested in this notion of intervention.
Yeah.
And how important that is to any notion of governance.
Yeah.
And this is the kind of thing that begins to take steps in that direction.
Yeah. So you'll have a lot more questions, I'm quite sure, because.
But when you're surrounded by mathematicians, you can. It's really hard to get positive feedback. They will always ask, "Can you prove this?" Or "What is the theoretical result?"
Yeah.
Yeah, but just relate to the question about Professor Sloot, that what is the theory, for complexity? I think I think it should be a theory that can, just like a theorem that can help us to understand the system, but it seems very difficult. It's still, I mean, for me now to see there can be a theorem that can tell a lot of things about complexity or complex system. But maybe, I don't know, I think the mathematicians want something like that, but I don't know when.
If I were you, I wouldn't be worried about that. I would let the mathematicians do what the mathematicians do. Let the physicists do what they do, and you do what you do. The point is that so often when we have, so I was studying early embryogenesis in certain species, and I was talking to physicists, and the first thing they do is come up with a very large set of differential equations. This is the way you describe the diffusion process, and that will lead to this kind of patterns. And then I asked them all the different terms in the equations, which actually did reproduce these patterns. But then I asked them what the meaning was of all these terms. I had no clue. So okay, they can come up with an equation, but that equation is actually meaningless, even though it can reproduce parts of this, these phenomena that we were looking into. So I wouldn't care too much about those mathematicians or physicists. And if you allow me, I'll have the mic. I'll already answer to the question, and then we can return the mic there. Otherwise, I'll be talking twice there. So for me, the thing that I actually learned by listening to all this thing, and also by getting answers to the questions that I posed, is it seems to me that at this point in time, complexity research is all about algorithms. It's all about thinking up some kind of cookbook to either reproduce the data or to predict things that we observe. Now, if that is true, then we might get back to the thing that Murray Gell-Mann told me like half a year ago when I met with him quite intensely in a one-day thing. He said basically maybe we should think of, if it's algorithmic, maybe we should think of algorithmic complexity. We should have, there is a huge reservoir of theory and methods out there by, for instance, Kolmogorov and Chaitin on algorithmic complexity. So maybe, and this is just what I'm taking away, what I want to think about the coming, whatever. Maybe if complexity is not mathematics as such, or physics as such, or descriptive as such, but maybe if it's algorithmic in nature, I think I want to think about, when I think about the theory of complexity, maybe that could be a theory of, algorithmic theory of complexity. Like I was trying to use information theory to understand the controllability of networks, maybe algorithmic theory can be something to worthwhile. That's what I will take away. Chris.
So, I feel like I'm, what did you do on your summer vacations?
Yeah.
But
what did you do?
Yeah, well, I didn't have one. So the first, I have two comments actually, and the second one is remarkably related to what was just mentioned. But the first one was, I thought, right at the outset, I wasn't sure what to expect, but when I heard the first presentation say that from the point of view of practice, at least, the motivation for Singapore to be interested and some sense of desire to have such an institute and study this topic revolved around people that have set up a system that is not so focused on long-term prediction or even prediction at all as it is on decision-making and incremental decision-making. I thought that this was really, really an important insight. I mean, like almost a shocking insight, and one that I have huge arguments with scientists about. And when you find out that you're used to beating your head against somebody else's head in this thing, and all of a sudden the whole you don't have to even have the discussion. I think it was really pretty surprising, and I thought incredibly reassuring, because I really do believe that's what it comes down to. I mean, either the system is planning for such complicated environments, acknowledges the fact that that you make your way through them, that the world branches, you stay on the branch, you understand that, and you understand to some extent what your alternatives and missed opportunities sometimes could have been, and you learn from that as well as what actually happened. This is very hard for scientists who depend on data that actually happened to adopt, but it is very common for decision makers and other creative people to deal with, to incorporate these kinds of ideas in a process that is not only in a potentially a world-class new institute, but also embodied in actual process. I found to be, I mean, pretty reassuring about Singapore, and also very interesting about maybe the state of what a complexity science might eventually turn into. As far as, but I think that this question that she raises beyond this personal issue of your unfortunate collaborators, but they're, you know, computer programs, especially the kind of simulations, at least that I do, and many of them that I heard about here, certainly the ones that possess interacting agents. I'll just call them interactionist computations. But really, everything of this kind has this property of being a linguiform object, right? I mean, whether or not it applies to something as a semantic referent, whether it's a market or whether it's something else, that aside, it's a linguiform object. And as a linguiform object, it has a natural imperative to be described mathematically, because it is a mathematical object. It is a linguiform object. Now, that doesn't mean it's a simple one, and it doesn't mean that its outcomes are going to be anything other than, from a computational point of view, something that's like just, you know, wildly intractable. But I think that if we use these methods, if we think that we can take little things that interact with other little things and put them in computers, and then for a moment we'll suspend disbelief and pretend that this really is a person that has an infection rather than just some linguiform thing interacting with other linguiform things. If we just forget that part, just think about then there is an enormous opportunity for theoretical innovation associated with understanding how those things work. And until we understand how those things work, I find it pretty hard to think that from a scientific and not just a mathematical point of view, from a responsible point of view, how we have a whole lot of a potential to map them onto something else effectively. And so I would say that from a mathematical point of view, at least, you know, I selfishly say this has been my mathematical point of view, is I focused very hard on studying large-scale interactions mathematically. And I studied them as linguiform objects, but that doesn't necessarily mean that I think this is a grand theory. In fact, it's a quite restricted theory, but it has to do being with the theory of our descriptions. If we're saying that these computer programs describe, represent, whatever you want to call it, something else, and we need a theory of our descriptions, I don't think that's too much to ask, or theories about our predictions. And I think that that's really potentially an interface that you could agree with your friends on. I don't know if you'll ever agree with them about if you point out of the program to something that it applies to, then I don't know how you prove that necessarily until we understand our descriptions. But anyway, so these two things, I think that the imperative for the program, I think it's just right. I mean, I was really horrified. I was waiting to be horrified to hear on day one that our goal is to take all this complicated stuff, the economy and the future of, I don't know, the rainforest and people and everything, and predict it. And I was going to just climb under the table and just wait for it to end. But it didn't start that way, and I was really, really happy about that.
We have 2 more minutes.
Okay.
And
my 1-minute version is just going to be that when I go home to my colleagues, I'll be glad to say that I met some people who I did not know before who have drunk the complexity Kool-Aid and who know what it's about, and they're going to do something of interest. It strikes me that in the same way that I have many colleagues now at George Mason, because we have a Center for Social Complexity, who are doing things that are not what SFI does or did, because we're all folks in social science when we're 40 strong. I would say that it's great to have, I'll tell my colleagues that you guys have an opportunity to do something which is also quite different from what Santa Fe did potentially, because you do have, in fact, a broad group of people here who with diverse interests and with deep knowledge and can do something hopefully quite different. And I wanted to say also too that from my point of view, the golden era of Santa Fe was in fact the era that Brian and John talk about, back when Stuart was there in the mid-90s to late 90s, when you really had biologists interacting with computer scientists, with economists, with physicists. And when SFI really fell on its feet, and I'm very happy to say this on tape, is that when SFI fell down was when you had physicists doing economics, and physicists doing computer science, and physicists doing biology, and physicists doing everything but physics. That's when SFI ceased to be of any interest, I think. And it's only when you mix the disciplines chemically, as Marx said many years ago, do you actually gain, I think, what complexity is about. I think that's good.
Well, I have minus 10 seconds left. And yeah. I can't talk quite as fast as Rob, but I can't think as fast as Rob does. Just some very quick comments. I was delighted to be here. For me, this is the end of a month at NTU, and I'm absolutely thrilled to see this group form under Jan and so many really exciting, really, really smart people pointing at you guys and some who are still have hangovers from last night. But keep up the work. This group's coalescing and is forming, and I'm just delighted to see that. One other quick comment I have is that for reasons that Rob just explained, I think I drifted away from complexity in the last 10, 15 years. I was thinking hard about technology and innovation, and came back to it only in the last year or so. And I have this kind of Rip Van Winkle impression of complexity. It's as if John and I and a few others, who got started to think hard about agent-based modeling in the late 1980s. And for me, it's a bit like the Wright brothers trying to figure out some fundamental things about flying machines. And then they go to sleep and they come back 80 years later or more, and there's a Boeing 787. I was blown away by what Chris and Rob and others were doing here, and Peter, of course. These models are truly sophisticated, and the thinking has deepened enormously and progressed. One last thing, the main thing I'm going to take away from this meeting is Peter's question. Is there a theory of complexity? And I think it's a completely profound question. The sort of good question that's almost like a koan in Zen. You can break your head against it. You can sort of think, is there? Yeah, there is one. No, there isn't one. No. My overall answer to this, and this is after thinking about it for 10 minutes, I think complexity as it currently stands is not unlike the discipline of philosophy. After 2,000 or 3,000 or 4,000 years, we still have no theory of philosophy, whether it's Chinese philosophy or Western philosophy. Why? Because philosophy is hard thinking about particular issues. And those issues, once they've been thought about, and if there are theories, think those theories go from philosophy into and start to make fields. There was a time when economics was nothing but philosophizing. When Newton, that was natural philosophy, became physics in due course. So I think it's the same in complexity, that a lot of these models will make their way into some of the older disciplines, be absorbed. It'll be forgotten where they originated from, many of these models. And we will still be left with a kind of residue. Philosophy still has the thoughts of Plato or the thoughts of Confucius and others that are still classics and haven't been superseded to this day. And I think I particularly liked your approach, by the way, Mr. Locke, if I have your name right. Sorry if I'm mangling it, but I do like this approach that there are motifs running across complexity, and you see these again and again. We got a lot of that from Neil this morning and from others. Some of these small things we're seeing about the formation of structures and about the propagation of change keep coming up again and again and again. So I disagree that complexity is going to disappear. The content will keep changing, morphing, and renewing itself, and that's probably perfectly appropriate with complexity, after all.
John, one last word?
Let's see. They say old guys get their ideas confirmed. I'm going to just make one comment that really amounts to taxonomy. And I saw this here. Sometimes it might have helped if we keep in mind that there, at least in my idea, that there are three broad classes of models. One class I'll call data-driven. And that is a kind of model where you try to make predictions. And the weather is a good example of a complex system in which we have a fair amount of data, we also have a fair amount of theory, and we try to make predictions. Okay, that's one class of models. That's quite different from what I call existence-proof models. An existence-proof model, the great example is von Neumann's proof that you could have a self-reproducing machine. It wasn't an attempt to look biological or anything else. It showed an existence proof that I could build a machine with certain well-defined mechanisms, and that changed the whole notion of what the definition of life is at that time, because that was, prior to that, that was taken, self-reproduction was claimed to be only possible for living systems, and so that distinguished living from non-living. So huge change in terms of existence proof. That's a very different kind of model with very different objectives, and somewhat related to that, but still a different kind of model. And I think several people here, Jing for one, this is where I have certain kinds of mechanisms, and I want to see what will happen when I put those mechanisms together. I call those exploratory models. Now, one can lead to the other. I can have an exploratory model, and that may lead to an existence-proof model, but they're distinct in terms of their original objectives and what you're doing. So I hold that it's important when you start tackling some piece of research, especially that involves modeling one way or another, that it's very important to decide which kind of model you're trying to build. And I saw that kind of distinction here several times. It was important, I think.
Okay, well, thank you all very much. Thank you all very much. I think we should applaud ourselves mostly. When I talked yesterday a little bit, I thanked everybody that was involved in the setting up of this workshop, so I won't do that again, but there's been a lot of people working very hard in making this such a great workshop. Thank you all.